Okay, so let's officially start, Kurt. Okay, so it's a privilege to introduce Andrew. And as it has become customary, I start with the baby pictures, and I will try to keep it under 55 minutes. Our story begins on a cold, rainy morning when we found the baby on the stairs of the IFA. We named him Andrew, and the rest is history. Okay, it's not entirely true. The rumors are false. In fact, Andrew has a loving family, and he was destined to a musical career. So here's a picture of his early musical career. But like all of us, he was not satisfied with classical music. He wanted to be a rock star. And like all of us, he joined a rock band with a questionable fashion sense. And that was the end of Andrew's musical career. And this is also where his story started to diverge from the narrative of an average astronomer. He could not resist the dark side, and he pursued a PhD in mathematics. I know, he tried to keep this secret, but now it's out. Astronomers love pictures and hate math. But he cleaned up nice. And after a stint of teaching, he actually finally started to study a PhD in astronomy. In fact, he was a NASA postdoc, a prestigious NASA fellowship, and an art scholar. And by the way, this is not the only picture I snapped at work, but this is the best one. I have more, and I have more pictures of our work life like this, for instance, and I could continue, but maybe it's enough if I say that we filled many, many whiteboards by Andrew's time at the IFA, and these whiteboards turned into papers, and lots of papers. In fact, just with me, Andrew has written 10 refereed papers, or at least under consideration. Some of them are still under consideration right now. So Andrew had an unmatched productivity at the IFA, I would say. And okay, let me turn a little bit serious now. Andrew did become a rock star in the end. So, and his work and his thesis speak for themselves. He came with a very unique background and with a PhD, and he has been one of the best and award-winning students at the IFA. Yet he was humble, and he stayed humble throughout. And while he could compete with the top talent in cosmology today, he decided to go back to teach high school students on the Big Island. And he'll be the most overqualified high school teacher on this side of the galaxy. In the COVID era, in fact, teachers risk their lives, but Andrew's choices always reflect his integrity. He walks his own path here on Mauna Loa. And finally, I finish with a nostalgic picture from a time when parties and dinners were possible. And I hope that, first of all, I hope that Andrew passes today. And if he does and COVID fades, I hope we can have him back for a talk at the IFA and celebrate appropriately in the near future. So thank you, Andrew, and take it away.
All right, thank you so much for that introduction, Istvan. Let me go ahead and share my screen now. All right, and thank you all of you who are, I was gonna say who came, but I can't really say that, so I can say at least thanks to all of you who have tuned in, and thank you for tuning in, even though this defense is going to be or is taking place a day later than it was originally intended. Anyway, mankind has speculated about the composition of the universe for thousands of years. You can go back about 2,600 years to Thales of Miletus, who speculated that everything is made out of water. Water is the fundamental element that underlies everything in existence. A couple centuries later, you had Aristotle, who disagreed with him. Aristotle said, no, there are 4 fundamental elements: fire, air, earth, and water. And that comprises everything terrestrial, but everything from the moon's orbit on up is made of this eternal 5th element, the ether, and we don't really have any direct experience with that 5th element. We don't really know much about what it is. And that could be seen as kind of discouraging because another tenet of Greek cosmology was that the Earth has the ratio of a point to the heavens. So in other words, all we understand is what's on the Earth. It is infinitesimal compared to the rest of the universe. And so therefore we understand essentially 0% of the composition of the universe. Fortunately, we have at least two advantages that the ancient Greek philosophers did not. One is the existence of telescopic instrumentation. With telescopes, we are able to observe objects that are fainter, that are smaller on an angular scale, and that emit in wavelengths far beyond anything that our unaided eyes could see. And this has the added bonus that because light travels at a finite speed, when we look far distant into space, we're also looking far back into time. And therefore, we can see, so to speak, snapshots of the universe as it has developed from the initial conditions to where it is today. The furthest away light or radiation that we can see, and therefore also the furthest back in time, is the cosmic microwave background, or the CMB, as I'll be referring to it maybe a few times in the rest of this talk. This is the incredibly uniform bath of radiation that impinges on the Earth from all directions with these little tiny variations that provided the seeds that could grow into the structures that we see today. So telescopic instrumentation is one advantage that we have, which the Greek philosophers did not. The other advantage is that we have physics. Okay, we know a lot more about what matter is, what radiation and light are, how they interact with each other. And by putting these two things together, the observation that we're able to make and our understanding of physics, we've come up with a concordance model for what the universe is made out of. So this is known as the lambda CDM model, or lambda cold dark matter. This model it manages to explain an entire host of observations with just 6 free parameters. And it tells us that the universe is made out of 68% dark energy in the form of a cosmological constant, about 27% dark matter, and 5% is the ordinary baryonic matter, the ordinary stuff that we see around us, the air, earth, fire, water of Aristotle. Only 5%. And like I said, this model manages to explain an entire host of observations. Let's see, there we go. It fits the statistics of the cosmic microwave background very well. And furthermore, if you start with the statistics of the CMB and you run a simulation and evolve it forward until what would be today, you get a configuration of galaxies and matter that is very similar to what we actually see around us. So in this picture, the red is the results of the millennium simulation, and the blue and the purple represent the observations that we see around us. And you can see they are extremely similar. So it seems that at this point, we can finally say that we have answered the question that perplexed the Greek philosophers. Now, we could say that. I'm not at all convinced that we should say that, because a lot of these terms are simply placeholders for our ignorance. For instance, what is dark energy? We say 68% is made out of dark energy, but we really have no clue what this stuff is. I mean, all we know pretty much is that it causes the expansion of the universe to accelerate. What is dark matter? We're not much better there. We know some things that it's not, or that we believe that we know that it's not, but what it actually is, so far we haven't been able to pin that down. There is a minor component of dark matter that's rather important that we do know some things about. That's the particle known as the neutrino. And we know that it has mass, a very small mass, but we don't know what that mass is. And then there's the Hubble constant tension. If you measure the expansion of the universe by looking at the cosmic microwave background and extrapolating forward to today, you get a certain number. If you measure the expansion of the universe by actually looking at the nearby galaxies and seeing how fast they're expanding, you get a slightly different number. And we have spent literally hours discussing this in our cosmology seminar. So we have a bunch of unanswered questions. And so it might be more accurate to say that we understand the composition of 5% of the universe, the 5% that's composed of ordinary matter. So in about 2,000 years, we've gone from 0% to 5%, which would be discouraging, except the pace of discovery has picked up in the last century. So hopefully we won't have to wait another 30 or 40 millennia in order to make up the last 95%. But in order to answer these unanswered questions, we have some surveys that are planned. We have some space-based surveys that are coming up, Euclid, Nancy Grace Roman Space Telescope, some ground-based surveys, such as the LSST at the Vera Rubin Observatory. And these galaxy surveys are designed to try to answer some of these unanswered questions. And so that raises the question of, how do these galaxy surveys help us answer these questions? So to understand this a little bit better, let's think about bread making. Okay? I have made bread from scratch exactly once in my life, okay, during quarantine, when everybody was experimenting with new things at home. And so I cannot say that I'm an expert at bread making, but everybody here has eaten bread, and we all know that the texture in the bread comes from the bubbles that are in the bread. And we know that different types of bread have different types of bubbles. And this characteristics of these bubbles reflect the ingredients that went into the bread. And in fact, if you knew enough about the process of bread making, you could probably look at the types of bubbles that are in the bread and deduce some information about the ingredients that went into the bread, as well as the process of how it got from the dough to the loaf. Well, in the same way, if we look out at the galaxies, we see that they're not uniformly distributed throughout space. In fact, they form structures that are similar in some ways to the bubbles in the bread. You have voids, and you have filaments, you have walls, and you have clusters. And just like the characteristics of the bread bubbles encode information about the ingredients of the bread, in the same way, the statistics of the galaxy arrangement, those statistics encode information about the ingredients of the universe. Because the fact is that we do know some things about universe making. It's called physics. And so we could say that we can take the arrangement of the galaxies plus what we know about physics, and we can deduce the ingredients of the universe. So what this question boils down to is, how do we take this, how do we extract this information that is encoded into the arrangement of the galaxies? How do we actually get at this cosmological information that is going to be inherent in the survey data? Okay, so what we do is we first of all form this statistic known as delta. Okay, up here we have, you could say, the cosmic web, the arrangement of matter in the universe, and at each point you can form the statistic delta. You take the density minus the average density divided by the average density. So delta equals 0 means that the density equals the average density. That point is neither over nor under dense. Delta equals 1 means at that point you have the average density plus that much again. Delta equals 2, you have the average density plus twice that amount. Delta equals -1 means you have the average density minus the average density, which gives you 0. So delta equals -1 means there is nothing at that particular spot. And so therefore, delta cannot get less than -1. You cannot be more empty than having nothing there. So that's the statistic delta. And then they form what's known as the power spectrum. Okay, for those of you who don't know what a power spectrum is, it's kind of similar to how our ears can listen to a piece of music. And even though several different notes are playing at the same time, our ears can break up the music into the distinct notes. In the same way, the power spectrum takes this arrangement here and it breaks it up into the amount, the number of large scale structures, you could say. Large scale on these diagrams are over on the left, and then the number of small scale structures, where small scales are over on the right. Okay, if you're used to looking at a periodogram is like the temporal version of the power spectrum, where the power spectrum here is spatial rather than temporal. Anyway, we look at the power spectrum because the power spectrum completely characterizes the field if the distribution is Gaussian. So we have theory that can tell us, all right, if you start with a certain cosmological model, okay, what is the power spectrum going to look like? And then you can compare that prediction with what we actually see. And if it matches what we see, we know that, hey, we've figured out what the universe is like. If not, we know that we need to actually change our model. Okay, and like I said, it completely characterizes the field if this distribution is Gaussian or bell curve shaped. One way to see this is to think of a one-point Gaussian distribution. It's totally characterized by the mean and the variance. Well, the mean, we have forced it to be equal to 0 by our definition of delta. So all the information is in the variance, and the variance is precisely the integral of the power spectrum. So if the distribution is Gaussian, you can look at the power spectrum, you can match it with observations, and that extracts all of the information that is there in the arrangement of the matter. So Sounds like our task is done. But of course, things are never that simple. And so there are at least 3 problems with using the power spectrum to extract information from the arrangement of the galaxies. The first problem comes with the condition that is stated at the bottom of the screen. If the distribution is Gaussian. The first problem is non-Gaussianity. Back at the beginning of the universe, everything would be Gaussian. Okay? Everything is fairly smooth, everything is bell curve shaped. As time goes on, gravity pulls matter into overdense regions, forming clusters. It pulls that matter out of underdense regions, forming voids, and so everything gets more clumpy. And so the power rises. And on large scales over here, everything stays Gaussian. Okay? Everything stays normal shaped, and you end up with the power spectrum just increasing linearly. But on small scales, you can see it doesn't have the same shape. You've got this nonlinear bump here. And the reason for that is on these small scales, you run into a problem. As gravity pulls matter into overdense regions, there's no limit to how overdense something can get. Okay? There's no limit to how much matter you can have there. But there's a definite limit to how underdense something can get. You can't have less than nothing. This delta has a hard cutoff, like we said, at -1. And so this is nonlinear growth. And as a result, you end up with a very non-Gaussian distribution because of this long tail and this hard cutoff at -1. And because of this non-Gaussian distribution, a lot of the information is in the higher moments of the distribution, which means that there is significant information that escapes from the power spectrum. How much of information fails to be captured by the power spectrum? Well, I was able to quantify this in my 699-2 project. Over here, this is the information for a certain parameter known as sigma 8, which describes the amplitude of the power spectrum. And in cyan, I'm showing the information that would be contained at various scales if you have a Gaussian distribution. In the magenta, I'm showing the information contained at various scales if you have a non-Gaussian distribution. And you can see that the difference, over at over at large scales, everything stays Gaussian. The power spectrum contains all the information. But over on smaller scales, on these small translinear scales, you have a distinctly non-Gaussian distribution. There's significant information, in some cases up to an order of magnitude, that escapes from the power spectrum. Up until now, this has not been a problem with galaxy surveys because the galaxy surveys until now have focused on the large scales. But these upcoming surveys, they want to press down into these smaller scales. And when they do that, the power spectrum is not going to capture the information. And that's a problem because we're spending hundreds of millions of dollars on these surveys, and we want to be able to get all the information that is inherent in the data that they return. So that's one problem, is non-Gaussianity. Second problem is the fact that galaxies are discrete tracers of the dark matter. We don't actually observe the dark matter directly. The galaxies are like little tea candles on the waves of the ocean. And we see them, we don't actually see the dark waves of the ocean. And so because they're discrete, we actually have to form another statistic, delta G, for galaxies, defined the exact same way, except instead of the density, you put in the number of galaxies. And this is discrete. N can be 0, N can be 1, N can be 2, can't be anything in between those. And so this is another problem with the assumption that everything is Gaussian and smooth like that. There's a third problem, it's called galaxy bias, and that's the fact that galaxies cluster more strongly than the dark matter. And you can see that this is going to be a problem because we want to extract cosmological information from the arrangement of the matter. And if galaxies are arranged differently than matter, and if we're observing the galaxies, then we somehow have to model that difference between the galaxy clustering and the matter clustering. So we have these 3 problems. There's actually a 4th problem that I will tangentially allude to near the end of this presentation. But these are the 3 that this dissertation deals with. So how do we handle these problems? Well, the main one is the non-Gaussianity. And so what we do is we turn to the field of sufficient statistics. What's a sufficient statistic? It's an observable that's capable of extracting all the cosmological information that is there in the field. Okay, the standard statistic, delta, you form its power spectrum. That is not a sufficient statistic because at these small scales that we're interested in, it loses a bunch of information. But Karen and Sopudi showed in 2013 that the log transform is a very good approximation to a sufficient statistic for typical cosmological fields. So what that means is we can, instead of taking delta, we can take the log of 1 plus delta and get this statistic known as A. the statistic A is a sufficient statistic, meaning that its power spectrum encodes, extracts virtually all of the information that is inherent in the field. And that's what we want to do. We'll see that there's a modification we need to make to A to deal with discreteness. For discrete fields, A star is the sufficient statistic, and we'll talk about what that is later. But in general, what we have in this dissertation is a sufficient statistics toolbox. Okay, to address these three problems, this dissertation forges 6 tools to address it. So the first problem was the non-Gaussianity of the dark matter. And so the 2 tools that address this are a prescription for the power spectrum of A and a prescription based on that for the matter distribution, the probability distribution of matter. And one comment on notation here, it's an unfortunate fact of life that power and probability both begin with the letter P. And so to distinguish them, when I'm talking about the power spectrum, I will use normal serif font. When we're talking about probability, I'll use a script type font for the probability distribution. Hopefully that can keep them a little separate. The second problem was the fact that galaxies are discrete traces of the dark matter. And so to address this problem, what we have is a prescription for the A star power spectrum. A star being, remember, the sufficient statistic for the galaxies. And then to address galaxy bias, we have 3 tools. First of all, we show that you can use this probability distribution to handle bias on the large scales. Next, we provide a model for the bias on the small scales after showing that it's problematic to use the same thing from large scales on small scales. And then finally, to actually apply this model, what we need is the covariance matrix for counts in cells. And so this is what the rest of this talk is going to be. Everything up until now has been a rather lengthy introduction. And so one word before diving into the first of these tools, just about all the results that we're obtaining here are going to be used, are derived from the millennium simulation, okay, with the L galaxy semi-analytical model. And that at first sight presents a problem because the millennium simulation is just one cosmology. How do we know that these tools apply to all cosmologies, or at least all reasonable cosmologies? Well, the fact is the millennium simulation has been rescaled to simulate 2 additional cosmologies, the WMAP7 cosmology and the Planck 2013 cosmology. Those, together with the original millennium simulation cosmology, give us enough of a variety that we can be fairly confident that these tools are valid for any cosmology that is at least near concordance, anything that's not too extreme or too weird or too divergent from the standard understanding of how things work. All right, so with that in mind, let's go ahead and let's look at the first tool. The first tool is the power spectrum of A. Remember, A is the sufficient statistic for the dark matter distribution. It encodes all of the information. So what we need to do is we need a way of predicting, okay, if you start with a cosmological model, what is the power spectrum of A going to look like? We have that for the normal power spectrum. Up until this work, we did not have that for the A power spectrum, because once we can predict what it should look like, we can compare that prediction with observations and we can actually draw conclusions. So over here, I'm showing on the right, I'm showing the normal power spectrum is in blue. And you may be wondering what these jagged things here are over on the left. That's where you're getting to scales that are large enough that you're approaching the actual volume of the millennium simulation. And so as a result, you don't have enough K-modes to average over and you end up with a lot of cosmic variance. You're going to be seeing these jagged things on the left throughout this presentation, and then it becomes more smooth on the right where you have a lot more modes to average over. But in blue is the normal power spectrum. In dashed red is the linear power spectrum. That's what the power spectrum would look like if everything had grown in a linear manner. If you didn't have that hard cutoff at delta equals -1 and everything had just grown linearly. And then in solid red is the A power spectrum. And you can see that the A power spectrum has the same shape as the linear power spectrum. This is actually a fairly surprising empirical fact that it tracks it so well. Okay, but the A power spectrum, even though it has the same shape, is biased with respect to the normal power spectrum. And here comes another unfortunate thing. It's that we use the word bias in this dissertation at least 3 different ways. We've already talked about, or at least mentioned, galaxy bias, okay, where the galaxies cluster differently than the dark matter. Okay, and this is another type of bias. And all it's saying is that there's a difference in the height of the 2 power spectra. Okay, and we call this bias b squared of a, and we square it for conventional reasons. Okay, so, but anyway, it has the same shape, just this bias. So if we could nail down what this bias actually is, then we could predict the A power spectrum, because we have tools to predict the linear power spectrum. Okay, well, we said before that the integral of the power spectrum is the variance. So if they really are the same shape, then all we need to do to get the bias is get the ratio of the A variance to the linear variance. And we can get the linear variance easily enough. It's just the integral of the linear power spectrum, which we can get using theory. And so this problem boils down to characterizing the A variance. And so if you plot the variance of A for a bunch of different, these three different cosmologies, a bunch of different redshifts, a bunch of different smoothing scales, you see that it has a very tight relationship to the linear variance. So what is this relationship? Okay, if the matter distribution in the universe were log normal, you would have this relationship over here, that the A variance is log 1 plus the linear variance. And that's what you have with this dashed curve up here. You can see it gives you the same, it gives you the correct first order behavior, but it diverges when you get to larger variances. So what we want is we want a modification of this formula that preserves the same first order behavior, but gives us gives us a little more flexibility. And so we find this formula right here has the same first order behavior, has this extra parameter mu, and we find the best fit for mu equals 0.73. And so this is the prescription for the variance of A in terms of the linear variance. So what this means is from theory, we can get the linear power spectrum. From that, we can integrate it to get the linear variance. From the relationship I just showed you, we can get the variance of A, and thence the bias of the A power spectrum, and thence the A power spectrum itself. We'll be comparing this with Smith et al. 2003. Smith et al. Is the standard formula for fitting for predicting the actual power spectrum. For instance, in this figure here, I show the standard power spectrum in blue with the Smith et al. Fitting formula in dashed blue. And so if we can get as good as the Smith et al. Formula, we're great. Okay, and we'll note that this is actually a closer to an ab initio theory than the Smith et al. Formula, because we only have one fitting parameter to explain, this parameter mu. So how well does it do? Okay, it turns out that in this case, our formula is the dashed red line, which you cannot really even see because it's hidden by the green line. It's a very good fit. Okay, over here, it's a little bit off, but we find that by adding a slope modulation factor, you can predict the A power spectrum even more precise, and that's what this green is right here. And with this slope modulation factor, our prescription is as accurate as the standard Smith et al. Prescription for P of K. Over here, the solid lines represent our prescription, and then the dotted lines represent the Smith et al. Prescription. So we are as good, in some cases even better, with this prescription than the standard Smith et al. So this is the first tool, the power spectrum of A. The power spectrum of A contains all of the information that's encoded in the matter distribution, and so that's why we have this first tool. So let's move on to the second tool, which is the probability distribution of A. How is matter distributed in the universe? If I take a point at random, what's the chance of finding a certain amount of matter at that point? Okay, that's the probability distribution that we're looking at. And the fact is, the matter distribution is roughly, we said this before, roughly but not exactly log normal. Okay, if it were log normal, over here I'm plotting A, which is the log of the matter. So the log of log normal is normal. And so you should be getting a nice bell curve shape. And you see, you don't exactly have that. You have some noticeable skewness, even at redshift 2. And so what we'll do is we'll say, all right, it's roughly log normal, so we can characterize it by at least the first 2 moments, and then we'll add a third moment. We'll characterize the skewness, and we're going to see if that does a good enough job. So let's look at these 3 moments here. Let's take the variance first, because we've already done most of the work for the variance. Okay, we have the prescription for the A power spectrum. We can integrate that to get the A variance. Actually, it's even less than that, right? Because we use the prescription for the A variance to get the A power spectrum. Now, there is a little bit of subtlety involved. We do have to account for pixelation. We have to account for aliasing. Without those, you end up with either the dotted line here or the dashed line over here, as opposed to the theoretical curve, which is in red. But once you account for that, we have a prescription for the variance of A. So let's move on or move back, depending on how you want to think of it, to the mean of A. Okay, what does the mean of A actually look like? Okay, when the low variance limit, we can again say that, hey, it's approximately log normal. We would have this prescription, we would have this relationship if it's log normal. And that does give us the correct first order behavior. So we want to modify it and see if we can get the same first order behavior, but a little more freedom at the right-hand end. And so what we end up with is we propose this formula right here, and that gives us, again, a very good tight fit for predicting the mean of A in terms of the linear variance. So from the linear variance, we can get both the mean and the variance. So let's turn to the skewness. For the skewness, what we have to do is we take as our starting point the formula from perturbation theory for the skewness of the actual matter distribution. And we can see that that depends on NS. NS is the slope of the power spectrum. And so we're going to look for a formula that involves NS. We also have a pretty good idea that it's going to depend on the scale. It's going to depend on the variance of A. And the reason is because the log is a nonlinear transformation. So there's a definite scale dependence to it. And so we propose a formula of this form, one component that depends on NS, and then the variance of A raised to a power that depends on NS. We find that when we plot out the skewnesses, whether you want to think of it in terms of T3 or the actual skewness parameter, we find a very good fit by taking these forms for the expression and getting best fit values for A, B, D, and C. So the bottom line is we have formulas for the skewness, the variance, and the mean. Now, can we put those three together to get an actual probability distribution? So what we do is we say, if we were, when we actually measure the matter distribution, we're smoothing over the survey cell first. Okay? And so that means we're essentially summing the matter at a bunch of different points. Now, if you sum identically distributed independent variables, the central limit theorem says that you have a Gaussian distribution. But if they're correlated, and we know that the matter density is correlated, you end up with a lot of times an extreme value distribution. What an extreme value distribution is, it's the sort of thing that you would use if you wanted to predict, all right, what is the probability that the largest flood this century is going to be thus high? Extreme value. All right, and so we find that the generalized extreme value distribution, or the GEV, provides a very good fit. It is characterized by these three moments here, and here are the formulae for the probability distribution for GEV. And it's got three parameters. It's got the Xi, which is a shape parameter. It's got sigma GEV, which is a scale parameter, and it's got mu GEV, which is the location parameter. And they correspond to these three moments up here. The skewness is enough to give you the Xi. The variance, together with the skewness, gives you sigma GEV, and the three together with the mean give you the mu GEV. So we have, with these three and with the GEV distribution, we have a formula for the probability distribution of A. The question is, again, always, how well does this work? How well does the GEV distribution fit? Over here on the left, we have the cumulative distribution function. In red is the actual distribution. In blue is the GEV distribution. You can see that it's a very good fit. Okay, the dotted line in each of these cases is if you assume that it's log normal and you take a Gaussian distribution in A. Over on the right, we find the residuals between the two. We can see there is some structure there, so we're never claiming that this is a perfect fit. Okay, but we can see that these residuals are in general less than 1%. And if you look at the RMS residuals, you can see if you look at each of these three cosmologies, if you look at a variety of redshifts, if you look at a variety of smoothing scales, you can see that the RMS residuals in each case are less than 1%. And so sub-percent level prediction is good enough for us. Okay, we can also predict if we know the A probability distribution. All you have to do is change variables and you get the delta probability distribution. And so we do this for two different smoothing scales. The squares represent the actual data. The curves represent our prediction. Again, you can see there's a very good fit. And one more picture to show the goodness of it. Here's a histogram for the A distribution, again, at 2 different scales. And you can see that our prescription, which is the solid curve, does a very good job of describing this histogram right here. The other curves that you'll see, the dashed curves that fit well over here on the large scales, but not over here on the smaller scales, that's the prescription of Ullmann et al. And they take a different approach. To be honest, it's an approach that I actually like better than the approach that I took. Okay, they start from first principles and derive mathematically what it should be. The disadvantage, whereas our approach is very phenomenological. Hey, it makes sense that this would work, and so we try to fit it, and hey, this works. Okay, but the disadvantage is that because of their first principles approach, their prescription only works well on these large scales. As you can see, it does a good job fitting it here, but on small scales, it's noticeably divergent. Since we want to extract information from these small scales, we want a prescription that actually works for these small scales. So this is tool number 2, the probability distribution of A. Together, these handle the non-Gaussianity of the dark matter distribution. So now let's move on to tool number 3, which is the power spectrum of A star. Remember, we said the sufficient statistic for a continuous cosmological field is A, okay, the log of 1 plus delta. And that's what we've developed the power spectrum for. But we don't actually observe the matter. We actually observe the discrete field, the Poisson sampled field of galaxies. And the sufficient statistic for that is A star. What is A star? A star, it's the Bayesian reconstruction of A, given what we know about how A is distributed and given the observed number n of galaxies. So we have underlying dark matter in a survey cell, and that dark matter produces a certain number of galaxies. That's a stochastic process. There's some randomness in it. Okay, and the same amount of dark matter might produce 10 galaxies in one cell, 11 galaxies in another cell, and so on. But all we can observe is the galaxies. And so then A star is where we look and say, hey, there are n galaxies here. And so knowing what we know about the distribution of A and the observed number of galaxies, what is the most likely underlying value of dark matter, given that we observe 10 galaxies or given that we observe 11 galaxies? That's the best we can do in reconstructing A. And it turns out that that actually is the sufficient statistic for a Poisson sampled cosmological field. Here you can see 2 power spectra. In blue is the A power spectrum. In dotted green is the A star power spectrum. And you can see that on the large scales, at least, they have the same shape. But again, there is a shift in the amplitude. And so this represents yet another bias. And so now we have 3 biases that I promised you we would talk about. There's the galaxy bias, which we've mentioned but haven't really talked about yet. There is the difference between the actual linear power spectrum and the A power spectrum. That's the A bias. And now we have yet another bias, the difference between the red A power spectrum and the green A star power spectrum. In any case, that's one feature that we're going to have to model if we want to predict the power spectrum of A star. Another feature that we're going to have to model, besides the bias with respect to the A power spectrum, is this plateau down here. You can see the A power spectrum just continues diving on down at small scales, but the A star power spectrum experiences this plateau. And that plateau is completely due to discreteness. Okay, if you are familiar with the 1 over n bar plateau for Poisson sampled in Fourier space, that's exactly the same sort of thing. It's not 1 over n bar because of the nonlinearity of A star, but it's very similar to it. And then there's one other feature we need to explain, and that is the fact that if you take this A power spectrum, shift it down by the amount of the bias, add a constant in order to get this plateau here, you still have a slightly different shape down here in the intermediate regions. And so we have a slight shape change, and that is something else that we need to model. So let's look at these 3 features right here and see if we can get a prescription for the A star power spectrum. Okay, so first of all, the bias of the A star spectrum with respect to that of A. Okay, if we ignore what happens at smaller scales and we just assume that the A star spectrum is proportional to the A spectrum, then we can show that this formula here gives the bias. And how well does it work? Well, you can see that With these different number densities, you end up with a very good fit here at these large scales, which is where we care about the bias. It starts having problems down here at the small scales where you end up approaching that plateau. But with this formula, we can characterize the bias. What about the discreteness plateau? To handle the discreteness plateau, we need to go back and we need to think about what A star actually is. Remember, we start with A being the underlying dark matter density, or the log of it. That underlying dark matter density gives rise to a certain number of galaxies, and there are some randomness, some stochasticity in here, as well as some discreteness. And then we observe the number of galaxies, and we get A star as a function of n. A star is the reconstructed underlying dark matter density based on the number of galaxies that we see. So what we do is we want to split A star into two components. Okay, the first component we're going to call A tilde, and the second component we're going to call delta A star. And what A tilde is it is the expected value of A star given a certain A. Okay, given a certain dark matter density, what is the expected value of A star? It's going to give you several different values of n. Those several different values of n are going to give you several different values of A star. What is the average expected value of A star given that underlying dark matter density A? Okay, this encapsulates the nonlinearity of the transformation from A to A star. It has no discreteness in it, has no stochasticity. All of that is now localized into the other component, delta A star. Delta A star is the deviation of A star from this expected value of A tilde. It incorporates all the discreteness and all the stochasticity. So the bias that we just talked about actually applies to A tilde. Okay, and so we can get the A tilde power spectrum, a modulo the shape change we'll talk about in a little bit, by applying the bias to the A power spectrum. And then the power spectrum of this delta A star gives you the discreteness plateau. And we're able to show that this term right here is what gives you the discreteness plateau. Delta V is the size of the survey cell, and then it's multiplied by the difference between these two variances. And then we have formulae for these two variances over here. So what this means is that we now can get the bias of the A star spectrum, we can get the discreteness plateau, and now let's look at the shape change. The shape change, it requires several other parameters, and I won't go into the details of it because even talking fairly fast, time is running away. But I'll show right here that you have it includes a linear term, it includes even an exponential term, and with these terms right here in these parameters, we can end up characterizing the ratio very well. And so putting it all together, okay, we have a flow chart here that you start with cosmology. From that, you can predict the linear power spectrum, the A power spectrum, and the distribution of matter. From that, along with the sampling scheme, we can get A star and A tilde and the bias and all of these parameters. And finally, we end up with a prescription for the A star power spectrum. Okay, how well does it work? How well does it actually reproduce what we see in the simulated catalogs from the Millennium simulation? Okay, well, what we've done right here is I've plotted 9 different examples. We tried the 3 different cosmologies, several different redshifts, smoothing scales, a host of different number densities, and here I've plotted 9, not randomly. The first 3 are actually the number densities that would apply for Euclid and the Roman Space Telescope surveys. And we can see that on here, it matches very well. It is as accurate as the Smith et al. Approximation. And so just as far as the legend goes, the solid blue is the observed actual galaxy power spectrum in the Millennium simulation. The dashed blue is the Smith et al. Prescription. The solid green is the actual observed A star power spectrum in the Millennium simulation catalogs, and the dashed green is our prescription. And so our prescription is as accurate as the Smith et al. Prescription for the Euclid and Roman Space Telescope number densities. Now, I plotted some of the other ones because we wanted to examine, we noticed that there was some deviation and we wanted to examine, all right, where does this deviation actually take place? And it seems that the deviation takes place mostly in this intermediate regime right here. So there's more error at low number densities, but to have a problem with low number densities, you really have to get to where there are fewer than one galaxies, that there is fewer than one galaxy per survey cell. And you don't do that in a survey. If you have fewer than one galaxy per survey cell, you're going to make your survey cells larger. You also have more error at intermediate smoothing scales and at small redshifts. But in general, it's accurate to within 5%, and typically it is comparable to the standard Smith et al. Prescription. So this gives us the power spectrum of A star. Remember, the power spectrum of A star encodes all of the information that is available in the distribution of the galaxies. And so with a prescription for this power spectrum, we can compare what is predicted by a cosmological model with what we actually see and derive information about what the universe is actually like. So let's move on to the last four tools, which deal with galaxy bias. Okay, galaxy bias is the fact that galaxies cluster more strongly than dark matter. This was recognized by Nick Kaiser back in 1984. So we have the matter overdensity over here. We have the analogous galaxy overdensity over here. And you can see that if galaxies cluster more strongly than dark matter, one way we could handle this is by parameterizing the relationship between delta and delta gal. And it turns out that on large scales, what's called a linear galaxy bias works very well. And so with a linear galaxy bias, you just take the matter over density delta, multiply by a fixed parameter b, and then you get the delta galaxies. All right, so if this works well, what's the problem? Well, the problem is that the effect on the power spectrum of multiplying by b is just to raise the power spectrum. And so that means it is completely degenerate with the amplitude parameter of the power spectrum, sigma 8. Sigma 8 is a cosmological parameter. It's something that we want to know. It's something that we care about. We don't care about B, okay? B is going to be different for every type of survey. It's going to be different for every type of galaxies. And so we want to get sigma 8. We want to disentangle the two of them so that we can, I don't want to say throw away B because you still report it in the paper, but we really want sigma 8. And so how can we break this degeneracy? Well, I said they're degenerate in the power spectrum on linear scales. Okay, but the fact is, like we said, the probability distribution is not log normal. And so that means it's got a tail, it's got skewness, it's got information that is not in the power spectrum. So maybe we can use the probability distribution of the matter to get sigma 8 without B, or at least to break the degeneracy between them. And so what we do is we say, all right, let's rewrite the probability of finding n galaxies. We're going to write it as the integral of the matter probability distribution times the conditional probability distribution of getting n galaxies given a certain amount of underlying matter. And we're going to further make the assumption that this conditional probability is governed by Poisson statistics. So if we have the average number of galaxies given a certain amount of dark matter, then we can get the conditional probability of getting n galaxies given dark matter. And when we break it up this way, we find, first of all, we can get the probability of delta from tool number 2. Okay, we phrase tool number 2 as the probability of A, but all you've got to do is change the variables to get the probability of delta. And then for this n given this expected n given delta, you get that just from the bias model. Take these three formulae from the previous page, put them together, you get the expected number of galaxies is the average number times 1 plus b times delta. So sigma 8, cosmology, comes into here, and then the b, the galaxy bias, comes into here. And so with different values of b and sigma 8, we can predict what the probability distribution of n galaxies is going to be, and then we can match it to observations. We can perform a chi-square fit. There's one other thing that we do have to worry about here, and this is the fourth problem that I referred to but didn't explain earlier, and that's redshift space distortion. The fact is, of course, in galaxy surveys, we don't directly measure the distance to a galaxy. The radial distance is inferred from the redshift. And since galaxies are flying through space in clusters doing all sorts of things, that proper motion will distort the redshift and distort the measured radial distance. And so at the scales that we're looking at, these large scales, these linear scales, the main component to redshift space distortion is this Kaiser flattening. And we found that we can model Kaiser flattening in this way to get an effective sigma 8. So with that, what we can do is we can take this formula for calculating the probability distribution and we can fit it to what's observed. So we started with the millennium simulation saying, can we recover the sigma 8 and B in a millennium simulation galaxy catalog? And so what we do is we take a variety of values of sigma 8 and B. We find the chi-squared for each one, and then we determine the best fit values. Okay, and so what we find is the best fit value is down here, the white cross. The cyan cross is the actual directly measured value of sigma 8, the amplitude of the power spectrum in the millennium simulation on these scales. And then also the corresponding B galaxy bias. And we find that we recover the correct values in the millennium simulation to a little worse than 1 sigma, so about 1.2, 1.3 sigma. And we consider that consistent, and so that emboldened us to go on and try to actually apply it to data. So this is the first application to data in this dissertation. Okay, simulations are great and wonderful, and we can get a lot of information from them, but at the end of the day, they're just simulations. Okay, we want to actually apply this to the universe. And so what we did was we took the Sloan Digital Sky Survey main galaxy sample, and we smoothed it on these large 30 megaparsec scales, and we got the probability distribution and then did the best fit. And so the red points give us the probabilities, the counts in cells probabilities from the Sloan main galaxy sample. The blue curve is the best fit model in redshift space. And then the shaded blue region, the light blue curves actually are random cosmologies drawn according to likelihood to show us, to kind of give a visual impression of the spread in parameter space. Over here is the chi-squared diagram. The best fit value is sigma 8 equals 0.92 plus or minus 0.08. That's the 1 sigma range of variation there. Okay, in magenta down here is the Planck value for sigma 8, the Planck 1 sigma band for sigma 8. And we can see that we're consistent with Planck to about 1.7 sigma. We're better than 2 sigma consistent. And then the red curve with the huge error bars, we included as a sanity check. Okay, what this red, it's not the red curve, it's the red point. But anyway, what this red point is, are the results of Howlett et al. 2015, who took the same sample that we did, the same data, and they calculated B and sigma 8 using a totally different method, a totally independent method. And they actually modeled several other parameters as well, which is one reason why their error bars are a lot larger. But we find that, given their large size of error bars, we are nevertheless consistent with them. And so that served as a useful sanity check. So in summarizing this tool number 4, we can break the degeneracy between galaxy bias and sigma 8 on large scales by fitting to the probability distribution. Now, a lot of what we did is only applicable to these large scales. For instance, on smaller scales is a problem with linear bias. Okay, so the problem with linear bias, this delta galaxies equals B times delta, comes in the fact that this B is almost always going to be greater than 1, because we want to model the enhanced clustering of galaxies. So we want B to be greater than 1. But remember, delta cannot go below -1. And if you have a very empty point in space where delta is, say, -0.9, you multiply by a B that's significantly greater than 1, you're going to get a delta galaxies that is less than -1, meaning you have fewer than 0 galaxies there, which of course is nonsense, is non-physical. The same thing can happen if you expand to one term further and get a quadratic bias. You can still easily get delta gal equals or less than -1. And you might say, okay, we'll just ignore the voids, but that could be problematic because half the cosmological information resides in the voids. And furthermore, these expansions are not physically motivated. They're mathematically motivated, but not really physically motivated. And so for tool number 5, we're providing a new model for the galaxy bias on small scales. And so we're going to start with some assumptions, and these are just approximate assumptions. Okay, we're making these assumptions, we're getting a model from them, and then we're seeing how well does that model fit. If we have to go back and modify the assumptions, we can do that. But our first assumption is the galaxy formation is determined to first order by initial densities and local physics. So we are ignoring tidal interactions, We're just saying, hey, it's determined to first order by initial densities in local physics. It's local. Next, we're assuming that the subhalos hosting a given galaxy type are roughly equivalent to each other. Okay, a dark matter halo can host a bunch of galaxies, but we're defining a subhalo as to be something that can host only one galaxy. Okay, and we're assuming that the subhalos hosting a given type of galaxy are roughly equivalent. Next, we're saying that it's energetically favorable for a subhalo to host a galaxy because the release of gravitational potential energy as the material condenses into a galaxy provides an energetically favorable situation. And then finally, we're assuming the number of subhalos is proportional to the actual matter density. More matter, more subhalos makes sense. So with those assumptions in mind, let's turn to the Ising model of physics, okay, which was first applied to model ferromagnetism. In the Ising model, you've got two states that an atom or whatever can be in. There's interaction between the neighboring atoms or objects, and then you can have an external field that makes one state energetically favorable. And so let's see if we can map these assumptions onto the tenets of the Ising model. First of all, if we assume the galaxy formation is local, and that means that we can ignore any interaction between neighbors. So we can cross this out and we can talk about an interactionless Ising model. Next, if we say that the subhalos hosting a given galaxy type are roughly equivalent, that means that we can characterize the subhalo by either whether it's hosting a galaxy or not. And so that means each subhalo can be in one of two states. It can either host a galaxy or it cannot. And then if it's energetically favorable for a subhalo to host a galaxy, that plays the role of an external field that makes one state energetically favorable. And since the number of subhalos is proportional to the matter density, what we'll do is we'll normalize everything by the matter density to get this quantity m. Okay, m is the expected number of galaxies per unit dark matter. Okay, so if you have a certain amount of dark matter underlying, what is the expected number of galaxies per underlying mass? That's what we plot here as m. And when we formulate it this way, we find that this Ising model with these assumptions actually gives us a Fermi-Dirac distribution with three parameters. There's BI, we've got AT, which plays the role of chemical potential, and then you've got T, which plays the role of temperature. But we don't really have three free parameters because we have an additional constraint. Basically, you've got to end up with the correct number of galaxies that you actually observe. And so that reduces the number of free parameters down to 2. So that's the Ising model. Nice, pretty model. We want to see now, does it actually work? Doesn't matter how pretty a model is if it doesn't work, right? And so let's first of all test it with a millennium simulation. On the x-axis, we plot A, the log dark matter density. On the y-axis, we plot M, which is, remember, the number of galaxies per unit mass. And we find that at small scales, it fits much better. The Ising model fits much better than the linear or quadratic bias models. Here, the red points are the results of the millennium simulation. The blue line is the Ising model, the best fit Ising model, and then the green line is the best fit linear model. And we can see on these small scales here, the Ising model fits much better than the linear or quadratic, which are really standard models. Okay, at scales larger than 30 megaparsecs, the linear bias is a superior model. Okay, and we actually knew that already. Everyone knows that on large scales, linear bias is a superior model. What about at the intermediate scales? At the intermediate scales here, neither model seems to provide a good fit. Okay, but in any case, we can see that on the small scales at least, okay, 10 megaparsecs or less, you end up with a decisive advantage for the Ising bias model. Now we want to apply it to data. Does it actually work with survey data? But for this, we've got to be a little more subtle because, after all, we can't measure the dark matter in the actual survey. So we have to play the same sort of game that we played earlier, where we take the probability distribution, we break it down into the matter distribution and the Poisson component, and we can get the matter distribution from tool 2. Now we can get the expected number of galaxies from our bias model. We can try different bias models, and we can see which one fits. Okay, when we apply this to the millennium simulation, we see that we certainly can recover the fact that the Ising model is superior by using this method. So now let's apply it to survey data. First, we'll look at the 60 FGS galaxies. And so when we apply it to these galaxies, we find that here in blue is the Ising model. It is a significantly better fit, especially at the low end, than the green linear or quadratic bias models. And so that's encouraging to see that the Ising galaxy bias model works for this data. We also tried it again with a Sloan main galaxy sample. Here we took a smaller subset of the galaxies because we didn't want to have to worry about various completeness issues. And again, we see the Ising bias model is definitely superior, especially at the low end, but also to some degree at the large end, superior to the linear bias model. And so this is tool number 5, the Ising model for galaxy bias on small scales. Now, to actually fit this and get best fit values for the bias parameters, what we would need is tool number 6, okay? Oh, before we do it, let me, time's getting away, so I'll rush through this quickly, this tool number 5. We also applied it to the Cosmos 2015 galaxies. And the problem with the Cosmos galaxies is they don't have spectroscopic redshifts, they have photometric redshifts. And that photometric redshift ends up smearing, the error in the photometric redshift ends up smearing the radial position of the galaxies. And if you try to simulate that by adding a Gaussian error to one dimension in the millennium simulation results, you end up reducing the number of voids, reducing the number of clusters, and increasing the number of mediocre spots in the universe, which makes sense because you're smearing out clusters, you smear them into voids, and everything comes more towards the average density. If we try to fit these bias models to the Cosmos galaxies, you end up seeing the exact same thing. The best fit Ising and linear models, as long as B is greater than 1, show more voids than you're supposed to get, more voids than are observed. They show more clusters than are observed and fewer intermediate density areas than observed. So we conclude that in order to fit these models, we either need to have spectroscopic redshifts or we need to model the photometric redshift error. And we'll mention that briefly again in future work. But finally, let's talk about the covariance matrix for the probabilities, tool number 6. Okay, to properly fit counts and cells probabilities, you need to be able to estimate the error on the measurements and any covariance between the measurements. Okay. And so this is straightforward if there are no correlations between survey cells. Okay, if there are no correlations between survey cells, the error on the measurements or the variance of the measurement is the probability times 1 minus the probability divided by the number of survey cells. So the error goes as 1 over square root of n, as you would expect. And we got away with this in tool number 4 when we measured the bias of the Sloan main galaxy sample. We got away with this because on such large scales, the correlations are very small. But when we try to apply the Ising bias model to smaller scales, we're going to need to know what the variance is when you include the correlations. Because if there are correlations between neighboring cells, then you don't really have NC independent measurements. Okay? Because if you have 2 cells right next to each other, you measure the probability with this cell, and you measure the number of galaxies in this cell, those 2 measurements are correlated to each other. And it turns out that if you have correlations between the neighboring cells, then you get an extra term over here, which increases the variance. And this extra term depends on the volume average correlation function. Okay, to test it, we performed a fairly involved test that I won't go into the details of now. If you're interested, feel free to ask in the question and answer period. But what you have here, the solid points, well, the points with the error bars connected by the solid lines, those are the actual observed variances in the probabilities. The thin lines are the the thin lines are the predicted variances. And you can see that they are totally consistent within the error bars. The only other thing that I'll mention about this plot is that up here, the dotted lines show what the variance would be if you had no correlations. If you had no correlations, it would just go down as 1 over n. And you can see that in some cases, you end up with an order of magnitude or 2 larger variance than you would if there were no correlations. And so it's important to be able to include these correlations. Likewise, we can talk about the covariance between probability bins. You have a similar formula that has a correlation, cross-correlation free term, and then you have a term which depends on the volume average cross correlation. And likewise, we were able to test this. We can find that the test works very well, except on some of the larger scales and some of the bins, you have large enough error bars that really we're only comparing upper limits, but the upper limits are consistent. And then when we get to, when we have this, we can actually calculate some covariance matrices. And so on these large scales, we find that it is roughly diagonal as we assumed. There's a bunch of noise in here, and most of that noise comes from measuring the volume average cross correlation. And we're working on some techniques right now to measure that better than we were able to. So hopefully we can get rid of some of that noise. But we see on small scales, the covariance matrix looks quite different. It's almost featureless. Most of the covariance is concentrated in these rows and a little bit right here. Anyway, that's tool number 6. And so we can now step back and summarize what we've done. Okay, we have 3 factors that interfere with the extraction of cosmological information from the galaxy power spectrum. The first factor is the fact that the dark matter distribution is non-Gaussian. And we have addressed this with 2 tools. First of all, we have a prescription for P of A, the power spectrum of A, where A is the sufficient statistic for the matter density. We also have a cosmology independent prescription for the probability distribution P of A. The second problem, the second factor, is discreteness, that galaxies are discrete tracers of the dark matter. We have addressed this with another tool that provides a prescription for the A star power spectrum, recalling that A star is the sufficient statistic for the discrete sampled fields, such as the galaxies. And then finally, the third problem is the bias of galaxies with respect to dark matter. We've addressed this with the final set of tools. We show that you can use counts in cells to break the degeneracy of galaxy bias with the cosmological parameters. We've addressed it with another tool by formulating a bias model that applies to small scales. And finally, we've facilitated application of that bias model by providing the final tool, which is the counts in cells covariance matrix. So what is left to do for future work? As always, there's plenty left to do for future work, but I want to mention 3 things that we would like to be able to do if possible. And one is we would like to be able to extend the prescription for the probability distribution to deal with elongated survey cells. Okay, right now it deals with cubical survey cells, or you could use spherical as well, and it would work just as well. But once it starts getting sufficiently elongated, the prescription will break down. And elongated survey cells is exactly what we would need to model the photometric redshift error that we ran into when we dealt with the cosmos galaxies. What we need is we need to be able to model the smearing it out into an elongated cell and to deal with the probability in that way. So that's one prospect for future work. Another prospect for future work is we'd like to be able to explicitly incorporate galaxy bias into the prescription for the A star power spectrum. Right now, you could kind of do it in a roundabout manner. You could fit the bias models to the observations, recover the bias parameters, use those to rescale the counts to what they would be if it were strictly Poisson sampled, get the A star power spectrum from that, and then compare it. But it would be a lot easier and less error prone if we could explicitly incorporate galaxy bias into the A star power spectrum. And then finally, we'd like to develop a framework for handling finger of God redshift space distortions. Okay, on the large scales, all you need to worry about is the Kaiser flattening. On the smaller scales, you have another effect that becomes quite dominant known as finger of God that comes from the virial motion of galaxies and clusters. And in redshift space, it really stretches them out into these long, thin fingers, so to speak. And so in order to apply this to smaller scales, or really to do any cosmology, even with the standard statistics on the smaller scales, you need to be able to handle that redshift space distortion. So with that, I'd like to just quickly turn to acknowledging, thanking a whole bunch of people, and I apologize. I'm sure there are people I've left out. I assure you it was not intentional. But I'd like to thank, first of all, my advisor, Istvan Sopody, for untold hours of discussion, feedback, encouragement, ideas. Thank you so much. I'd like to also thank my other committee members, especially those who supported me financially during the summers, Harold Ebling and Dave Sanders. In general, I'd like to thank all of my professors and teachers here at UH, as well as Mike Nasser for his excellent supervision of me when I was a teaching assistant. Thank you, Mike, and thank you all my professors. Thanks also are due to Amy Miyashiro and Karu Uyehara for navigating the bureaucracy at UH for me, and especially Amy, who handled a bunch of flight schedules and reimbursement requests, always with a smile, and usually ending with me spending some time in her office watching her webcams that she has of nesting eagles, because she is an avid bird watcher and her enthusiasm for it is contagious. I'd like to thank NASA for the NESSF fellowship that supported my final 2 years of research. I'd also like to thank the Arts Foundation, National Society of High School Scholars for scholarship awards. Thank you also to the administration of Christian Liberty Academy for their support and their encouragement in the pursuit of this degree. The German Astrophysical Virtual Observatory hosts the Millennium Simulation, which is crucial, as you have seen, to almost all of the results in this dissertation. And I also want to acknowledge the very significant cultural role and reverence that the Summit of Mauna Kea enjoys in the Indigenous Hawaiian community. And I'd like to say mahalo au ya oko. Thank you to my fellow graduate students, both those who are still here and those who have graduated, for an awesome 7 years of collaboration and friendship, especially Connor McPartland, with whom I traveled to Copenhagen and New York and Hilo. Thank you to my ohana at Hawaii Kai Church for your support, encouragement, and fellowship. Thank you to my family for your love and strength. And then I also want to personally be thankful for the wonder of being able to study the universe in the first place. And I can express this wonder in no better words than the words of the Hebrew poet from 3,000 years ago, who said, "When I consider your heavens, the work of your fingers, the moon and the stars which you have ordained, what is man? And compared to the universe, what are we indeed? Little tiny specks of low entropy, highly alpha enriched baryonic matter that somehow has the ability, at least in part, to grasp the whole." And I find that nothing short of miraculous. Soli Deo Gloria. And so at this point, I will conclude the presentation and take any questions you might have.
Yeah, let's thank Andrew for his presentation. I think what we do now, we will take questions from the audience. So I think if anybody has a question, let's use the function here in Zoom to raise your hand. And I try to look. And okay, so Dave, do you have a question? I see.
Yes, can you hear me?
Yes.
Okay, Andrew, your problem number 3, galaxies cluster more than dark matter clusters, I think is the way it was worded. I did not know that we knew enough about dark matter to make such a statement. So could you quickly summarize what observational data we have that tells us about how dark matter clusters?
Okay, well, this was originally discovered back before, right now we can do some weak lensing, but it was deduced originally from the fact that if you have different types of galaxies, they cluster in different ways. And so that means that therefore the galaxies have to cluster differently than the dark matter, just because different types of galaxies cluster in different ways.
Okay, I'm a little confused now. Is it just that the dark matter clusters differently, or is it that it's clustering less?
Okay.
I thought the wording of your problem number 3 was that the galaxies cluster more than the dark matter.
That's right. So the galaxies cluster more strongly than the dark matter. The way to think of it is, of course, that the galaxies form at the peaks of the dark matter density distributions. But different types of galaxies will form in, some types of galaxies you could naively think of it would require a threshold in order to form, and others would require a higher threshold. And so those galaxies would cluster more strongly than these types of galaxies, which would cluster more strongly than dark matter in general.
Okay, thank you.
Can I ask everybody to mute themselves who are not speaking so we wouldn't hear? Okay, so the next, James, do you want to ask a
Yes.
question?
So I maybe don't have a strong grasp of what it means to be a sufficient statistic. Could you speak a little more of the concept and maybe give an example?
Well, it was very clear what he had done
Okay,
and why
so-
he had done it, or in terms.
all right.
Esther, can you mute, please?
So there's you can define the amount of information that is in a distribution by, it's what's called Fisher information. So it depends both on the partial derivative of what you're observing with respect to the parameter that you're trying to constrain. It also depends on the covariance, the variance of that parameter. And so you can calculate what, if you know everything that there is to know, then you can calculate how much information, how much Fisher information is actually in there. Now, different observables will capture some of that information. Some observables will capture all of the information, okay? A sufficient statistic is one that essentially captures all of the information, or we're gonna say in this case, its power spectrum captures all of the information. So just as the power spectrum of delta captures all of the information if you have a Gaussian underlying distribution, in that case, it would be a sufficient statistic. So that's why for the CMB, the power spectrum of the CMB is a sufficient statistic. CMB is very Gaussian, and this power spectrum captures all of the information. In other words, you could get as tight error bars on the parameters that you're trying to constrain by looking at the power spectrum of the CMB as you could any other way of dealing with the CMB data, okay? But for non-Gaussian distributions, like the matter distribution on small scales, if you try to get error bars by analyzing the power spectrum, your error bars are going to be larger than they have to be. Whereas if you use a sufficient statistic, you can get error bars that are as small as possible given the uncertainties of the underlying data. Does that make more sense?
I think so. Let me see if I understand this right. So let's say if we took random samples from a standard symmetric Gaussian distribution, then the most likely value, like a mean or median, would be a sufficient statistic for the most likely value. But if we have like a skewed distribution, then maybe a median might be a more sufficient statistic, and a median might not, or rather the median would be a sufficient statistic and the mean would not be. Does that make sense?
It makes sense, and I think it gets across the right idea, although it's not strictly true. But you've got the right idea that it gives you if you take the median of a class, that can oftentimes give you a better idea of how the class is doing than the mean would. And so yeah, that underlying concept is the right concept.
Okay, thank you.
Okay, Jeremy?
Hi, Andrew. My question was, did you have any, is there some physical reason or some physical intuition for why log of 1 plus delta contains more information than just delta?
Yes, essentially, if you start by thinking about the fact that the distribution is approximately log normal, okay? If you take the log of delta, then or log of 1 plus delta, you're going to get closer to a Gaussian distribution. So that it's not the fact that A actually contains more information than delta, because it's just it's a one-to-one transformation, okay? But it's the power spectrum of A that contains more information than the power spectrum of delta. So the when you're looking at delta, a lot of the information escapes into the higher order moments. It escapes into the higher order correlation functions. And in fact, there's a significant chunk that even escapes the whole hierarchy of endpoint correlations altogether. But when you look at the power spectrum of A, most of that information stays there in the 2-point correlation function. So it's because of the fact that the distribution is highly non-Gaussian that a lot of it escapes into the higher order moments. So again, it's not saying that A has more information than delta, but it's that the power spectrum of A captures more information than the power spectrum of delta.
Right, I see. Thank you.
Okay, thank you, Eric.
Yeah, hi, Andrew. Yeah, that was a really great talk. I guess kind of connected to the last two questions. Can you say a little bit more just about how you can actually establish that the power spectrum of A is a sufficient statistic?
Okay, so this was actually work that was done before I came. It was Karen and Sapudi 2013, and essentially what they did was they took the Fisher information formula, and then from that they constructed the actual exact sufficient statistic, which you can formally write down what the sufficient statistic would be. But then they showed that and that's going to be a lot more complicated than the log. But what they showed then was that for typical cosmological fields, as long as the n is close to -1, okay, for typical cosmological fields, the log is very close. So you've got you've got the Box-Cox transformations for different values of n, but they show that the log, which is n equals -1, does a very good job. In fact, if we were to go back to, let's see, it doesn't like this. Yes, it does. There we go. Where is it? Right here. Okay, so over here, the actual sufficient statistic would be this. Well, these three here. You've got the linear density, you've got the Box-Cox transformation, and you've got the log transformation. And they showed that the log transformation is very, very close to these. And that's how we established that in the sense of the power spectrum. Let me rephrase that. The second moment of the log captures just about all of the information that is in the second moment of the true sufficient statistic.
Okay, Lucas.
Hey, Andrew, great talk. Really enjoyed it. I had a question about the application of the Ising model to the data. I believe you said that at small scales, that's where the Ising model performs the best over the linear bias model, and at largest scales, the linear bias model outperforms the Ising model. But at intermediate scales, neither seem to reproduce the data.
Mm-hmm.
I was wondering if there was any physical intuition for why none of our models seem to work in that intermediate redshift regime.
That's a very good question. And to be honest, I don't really have a good answer for that. As far as linear bias, I don't even know if there is a good, I mean, there is physics behind the linear bias that you can get. I mean, you can derive it from perturbation theory. And so there is some physical basis for it. All I can say is that it's, when you get into those intermediate regimes, perturbation theory is breaking down. And then coming from the other end, some of our assumptions are breaking down as far as whether actually there is some, there is something else that's going on. We find that when we look at, let me back up. It turns out that the actual bias depends on information from a multitude of scales. Okay, it turns out that on the small scales, if you just look at the Ising model, that does a good enough job of capturing that information. But in the intermediate scales, it seems like you've got to combine information about the clustering from a variety of scales. You can't get it just by looking at, say, the dark matter on this scale. And so that means that some of our assumptions are breaking down. It's not strictly local. Okay, there is information that you need that comes from other scales. So that means that tidal effects matter. That means that non-locality matters. So that's what I would say is the ultimate answer. It's showing that there is significant non-locality in a way that means that you can't parameterize it just with Ising model parameters.
Great. I guess I have a follow-up question. would you prescribe to use to adhere with the linear galaxy bias at large scales? So say you're doing a study, you want to measure this as best as possible. Would you prescribe to use the Ising model on small scales and then something else in the middle, and then at large scales stick with the linear galaxy bias? Or do you think it's better to be consistent throughout, even though you know that the linear galaxy bias is a better estimator?
Well, I think if you're dealing with multiple scales, the different scales have different information in them, and so it would be good to handle the different scales using I would say it's good to handle the different scales using the bias model that is most appropriate on that particular scale. Because part of what the log transformation does is it's nonlinear, and so therefore it manages to pull in information from several different scales, you could say, effectively. Obviously, the log transform is local, but because there's a lot of scale dependence on the information, it's actually good to pull information from multiple scales. However, of course, you're going to, when you're trying to combine those and figure out what the covariance between them is in order to get your final error bars, that's going to be quite a task, I guess. But it's what ultimately ought to be done.
Great, thank you. Again, great talk.
Thank you.
Okay, thank you. Michael?
My question is, you mentioned that the matter distribution is governed by a log normal distribution. Can you explain exactly what that means over what scales and why it should be that way, I guess, physically?
Physically, you can get the log normal distribution if you make some simple assumptions at the outset. Simplifying assumptions, I believe it was Coles and Jones that showed this. And right now it's slipping my mind exactly what those are. I think it has to do with the velocity being proportional to the gradient of the matter distribution. As far as what it actually means, well, one thing it does mean is that when you project everything on the sky, the two-dimensional projection is very, very, log normal is a very good approximation there. It's when you get to when you're actually looking at the 3D distribution on smaller scales, the log normal approximation tends to break down. I don't know if that exactly answered your question.
Mostly. I got the half of it about the velocity following the gradient that leads to that. But I guess over what scales is it true as well? I mean, it's not true on the scale like a human.
Oh, no. Okay. So yes, we're talking about like scales down to 2 megaparsecs.
2 megaparsecs up to gigaparsecs.
Yeah, up to, when you up to say 30 megaparsecs, it's still pretty close to log normal. Okay. In fact, it's much closer to log normal on those scales than it would be on the smallest scales.
And so, and then after sort of 300 megaparsecs, you're in the uniform sort of limit, or?
Yeah, at that point, things are even more nearly Gaussian than log normal. So you're starting to even lose some of the log from the log normal.
Okay, thank you.
Okay, any other question from the general audience? Exxon, do you have a question? Okay, for a second I've seen Exxon's hand up, but it's down now, so I'm assuming there is no more question. Oh,
Hassan has a question in the chat.
Oh, okay, sorry. Okay.
He said, you said that the linear P of K doesn't hold all the information, but later you started from P of K to regenerate P of A star. The question is, how do you get more information from P of K? Okay,
that's a very good question, because if we could actually measure the linear power spectrum, that would have all of the information in there. Because the linear power spectrum is what you get if you start with your original distribution and just everything grows linearly. So that preserves all of the information. It's the nonlinearity that ends up making it non-Gaussian. And so that's why we can start with the linear power spectrum, and then we can get the, then we can essentially undoes the nonlinear growth. And so that's why that's part of the reason why we can get this from the linear power spectrum, because it hasn't lost the information. The problem is we can't actually measure it, right? We can theoretically predict it, but we can't look in the universe and measure the linear power spectrum because everything has grown non-linearly.
Okay. Any other question? Okay, so if there is no more question, I'd like to ask all the general attendees to sign off, and we keep the panelists, the committee, and Andrew, and we will be greeting Andrew. So thank you all for attending this talk.